Hey everyone, and welcome to my channel. In today's increasingly interconnected world, the efficient and stable delivery of electrical power is paramount. As our energy needs grow and the power grid becomes more complex, the significance of power system stability analysis takes center stage. If you find this video helpful, consider supporting us. Let's get started. From ensuring the reliable operation of our electrical infrastructure to mitigating the impact of disturbances and maintaining a steady power supply. Simply put, it asks the ability of a power system to withstand various disturbances and return to an acceptable state without any long-lasting negative effects. One fundamental concept is the rotor angle, which represents the angular position of a generator's rotor relative to the infinite busbar, a reference point representing the rest of the synchronized generators. In a stable power system, the frequency remains constant and in sync with the reference. Traditional approaches include the swing equation analysis, which describes the dynamic behavior of a power system using nonlinear differential equations, and time domain simulation using programs like PSASP or ATP, which simulate the system's response over time, and MATLAB, which help engineers analyze and model power systems to predict their stability under various conditions. Take, for instance, the well-known case of the 1996 Western Systems Coordinating Council WSCC stability study. These critical elements were found to be more vulnerable due to factors such as their location, capacity, and the overall system loading. The study's findings were instrumental in prompting grid operators and policymakers to prioritize measures aimed at enhancing the overall stability of the power grid. This includes investments in transmission infrastructure, implementation of more robust control systems, and the development of contingency plans to address potential stability issues. These criteria provided a quantitative basis for evaluating stability margins and assessing the adequacy of system protections. For example, the need for enhanced communication and data sharing highlighted in the report has spurred the adoption of advanced metering infrastructure and real-time monitoring systems. These advancements allow for more precise and timely assessments of system conditions, enabling operators to take proactive measures to maintain stability. The study's comprehensive approach, stakeholder involvement, and focus on practical recommendations have had a lasting impact on the power industry, contributing to a safer, more reliable, and stable power system. Additionally, the study highlighted the need for enhanced communication and coordination among system operators across the interconnected grid. We can continue to enhance the stability and reliability of our power grids, ensuring a sustainable and secure energy future. We hope this video has provided you with a solid understanding of the key aspects of power system stability analysis. Please don't hesitate to share your thoughts, experiences, or suggestions in the comments section below. If you enjoyed this video, give it a thumbs up and subscribe to our channel for more insightful content. Thanks for watching. As technology advances, we can expect even more sophisticated methods and tools to emerge, enabling us to monitor and control our power systems more effectively. The increasing integration of renewable energy sources, such as solar and wind, which exhibit inherent variability, poses new challenges for power system stability. Stability analysis techniques must evolve to address these challenges, ensuring that the grid remains stable and secure. Furthermore, the widespread adoption of distributed generation and smart grid technologies requires innovative stability analysis methods that can effectively monitor and coordinate these dispersed resources. As power systems become more complex and interconnected, the need for robust stability analysis techniques becomes ever more crucial. By identifying critical system elements and potential vulnerabilities, the study has guided utilities in prioritizing investments to strengthen grid infrastructure and enhance stability. This has resulted in targeted upgrades to transmission systems, improvements to generating unit controls, and the implementation of more robust protection schemes. The findings of the NPCC study have had a profound impact on the stability assessment practices within the power industry. The study's recommendations regarding stability criteria and system protection have been incorporated into industry standards and regulatory requirements. Furthermore, the emphasis on coordinated system operations has led to the development of joint protocols and procedures among neighboring utilities and system operators. The study also highlighted the importance of maintaining adequate levels of reserves, both in terms of generating capacity and reactive power support, to mitigate the impact of potential disturbances. This massive study, conducted by the NPCC, involves extensive collaboration among various stakeholders, including utilities, independent system operators, and regulatory agencies. Its primary objective was to evaluate the stability of the Eastern Grid under a wide range of operating conditions, considering both normal and contingency scenarios. The NPCC study encompassed a significant portion of the United States power grid, incorporating various types of generation, transmission, and load characteristics. Through extensive modeling and simulation, the study assessed the system's response to potential disturbances, including the loss of major generating units, transmission line outages, and sudden changes in system loading. Based on the findings, recommendations were made to enhance the stability of the power grid, including strengthening certain transmission lines, diversifying power supplies, and implementing advanced control strategies. This comprehensive investigation examined the stability of the Western United States power grid, encompassing a vast interconnected system covering multiple states. The study, conducted by the Western Systems Coordinating Council, WSCC, was prompted by concerns regarding the growing vulnerability of the grid to disturbances. As the power grid became more interconnected and subjected to varying loading conditions, there were increasing worries about its ability to withstand potential faults or sudden changes in power generation or consumption. The main objective of the WSCC stability study was to evaluate the overall stability of the Western U.S. power grid under both normal operating conditions and various contingency situations. This involved assessing the system's response to potential disturbances such as the loss of major transmission lines or generating units. Through extensive analysis and modeling, the study aimed to determine the system's resilience and identify potential weaknesses or areas susceptible to instability. By simulating different scenarios, these software programs provide invaluable insights into the system's behavior and assist in identifying potential weaknesses. These methods provide valuable insights into the stability characteristics of the power system. However, they have limitations in terms of speed and accuracy. However, disturbances such as sudden changes in load or generation can cause the frequency to deviate from the set value. One notable technique is the use of Phasor measurement units, or PMUs, which are specialized devices for synchronized and high-speed acquisition of phasor measurements. PMUs provide real-time information about the system state, enabling better monitoring and control. Wide area monitoring systems, WAMS, leverage the data from PMUs to provide a broader view of the power system's stability state. They enable system operators to observe stability-related parameters across the entire network, facilitating early detection of potential issues. Moreover, the integration of phasor measurement units and wide area monitoring systems has revolutionized power system stability analysis by providing real-time visibility into critical stability parameters. With synchronized and high-speed data acquisition capabilities, PMUs offer precise measurements of voltage magnitudes and angles, allowing for accurate monitoring of rotor angles, frequency deviations, and other key stability indicators. WAMS leverage the vast amount of data collected by PMUs to provide comprehensive system-wide views, enhancing the ability to detect and analyze stability issues. The combination of PMUs and WAMS allows for more effective planning, operation, and control of the power grid, ultimately contributing to a more stable and reliable power system. For instance, if the system experiences a significant increase in load, the frequency may drop as the available generation does not match the increased demand. On the other hand, if generation exceeds load, the frequency may rise above the set value. In the realm of power system stability analysis, understanding frequency dynamics is crucial. By monitoring and analyzing frequency deviations, system operators can gain insight into the balance between generation and load. This analysis helps identify potential stability issues, such as system-wide instability or localized voltage collapse. The rotor angle determines the relative motion between the rotors of different machines in the power system. When analyzing transient stability, deviations in rotor angles play a crucial role in determining the system's response to disturbances. The rate of change of these angles, known as the angle's derivative or delta, provides insights into the system's dynamic behavior. In the context of transient stability, the angle's derivative reflects the speed at which the generators are accelerating or decelerating due to disturbances. By monitoring and analyzing the rate of change of rotor angles, power system stability analysis can effectively assess the system's ability to maintain synchronism and prevent potential instability issues. Imagine your local power grid as a vast network of interconnected components working harmoniously to deliver electricity to your homes and businesses. Power system stability ensures that when unexpected events like sudden changes in load or equipment failures occur, the grid remains resilient and continues to deliver electricity reliably. Power system stability analysis is the backbone of a resilient and dependable electrical grid. So let us dive into this essential topic and explore its pivotal role in shaping a reliable power future. But before we start, please subscribe to be notified of the release of our upcoming videos. To grasp the essence of power system stability analysis, we must first define what constitutes power system stability itself. There are three primary types of power system stability, each focusing on a different aspect of grid reliability. Transient stability, also known as dynamic stability, deals with the system's behavior immediately after a major disturbance, such as a three-phase fault in a transmission line or a sudden change in load. The focus here is on the ability of the system to maintain synchronism, meaning the generators continue to operate in harmony, producing a stable output. Steady-state stability, on the other hand, examines the system's behavior under steady operating conditions. It assesses the system's response to gradual changes in load or generation and focuses on maintaining voltage stability across the grid. Voltage stability is a critical aspect of power system stability that addresses the system's capability to maintain acceptable voltage levels under various operating conditions. Voltage collapse, a severe form of voltage instability, occurs when the voltage at a critical point in the system drops below a certain threshold, leading to a blackout. Let's now delve deeper into some key concepts that form the foundation of power system stability analysis. Another important concept is frequency deviation, which refers to the difference between the actual frequency of the power system and its nominal or set frequency. Now that we have a solid grasp of the fundamentals, let's explore the various methods employed in power system stability analysis. As technology advances, new and improved methods have emerged. These advanced tools are supported by powerful software like the Power System Analysis Software Package, PSASP. To truly appreciate the importance of power system stability analysis, let's look at some real-world examples where it has been instrumental. One notable finding of the WSCC study was the identification of several critical transmission lines and generating facilities whose outage could potentially lead to instability issues. Moving forward, the results of the WSCC stability study served as a foundation for subsequent stability assessment efforts. Another remarkable example is the Northeast Power Coordinating Council (NPCC) study, which focused on the stability of the Eastern Interconnected Power System in the United States. One of the key outcomes of the NPCC study was the development of stability criteria and guidelines specific to the Eastern grid. The study's insights have also contributed to improvements in power system control and monitoring. Moreover, the NPCC study has played a pivotal role in shaping the planning and investment strategies of power utilities. In conclusion, the NPCC stability study stands as a landmark achievement in power system analysis, providing invaluable insights into the stability characteristics of the Eastern interconnected grid. As we progress further into the 21st century, power system stability analysis will continue to play a vital role in ensuring the reliability and resilience of our power grids. By understanding the fundamentals, exploring advanced tools, and learning from real-world applications.
So now, a bit about me. My name is Mike L., and I am an experienced electrical engineer who has worn many hats, holding key roles in projects, engineering, planning, operations, asset management, maintenance, and field resources development. I design and pioneer engineering solutions to propel the utility and energy industry forward. My passion within the industry has also driven me to develop educational materials for the new generation of utility and energy professionals. The knowledge I teach is not only based on my own experience within the power utility industry, but also on knowledge gaps identified by other professionals in the field. Learning from me will provide you with the comprehensive, fundamental knowledge you need to kickstart your professional career in the utility industry. If you are interested in what I have to teach, check out my courses at Udemy and connect with me on LinkedIn, X, and Facebook. Don't forget to comment, like, and subscribe this video. Bye for now.